Greetings everyone. Today we're going to talk about the power amplifier for my tower mounted 10 GHz narrowband system. I bought this amplifier from a good friend, a ham radio friend, and got it at a really reasonable cost. There is some work to put on it because this is an Alcatel MDR 8000 power amplifier. So it came from a microwave point-to-point link, a commercial grade microwave link, and it was originally operating from 11.2 to 11.7 gigahertz. And so I need to retune it to 10.368 gigahertz. And I'll show you what I've done so far. So the actual amplifier itself is this box here, the part in the middle. That's the amplifier with its input and its output port. And there's a monitoring port right here, another SMA also that can be used to monitor the output power, though there is a power detector inside and it provides a DC voltage to indicate the output power as well. So the actual amplifier is this. The long board here on the right is the support board. When this amplifier was inserted in a real system, it was attached to this board here, and this board would connect to a backplane, and it made a full microwave transmission system. But that's not the board I'm going to be using it with. I've purchased from VA3TO this board here that basically replaces the whole Alcatel board. This mounts underneath the amplifier, and it will reduce the size requirement to make this amplifier work. It's a 3-stage amplifier. It requires negative gate supplies on those FETs inside, 3 stages, so 3 separate biases, plus the drain voltage, which is around 10 volts, and that will be fed here. There's a MOSFET to switch it as well. So that's going to be much smaller, and it's going to be great. I've ordered the parts already. I need to assemble this thing. So for sure, I'm going to give you an update later once everything is put together. For now, what I've tried to do is to optimize the gain of this amplifier. So I've hooked it up, plus 10, minus 5, minus 12, 3 supplies that are sent to this board. When it was inserted, I believe it was plus 10.5, but providing 10 volts is sufficient. I need at least 7-8 amps of 10 volt, which is what I get with a switching power supply. And the actual gain that I got at 11.4 gigahertz was 18 dB, which is less than what was done by other hams to optimize this thing. You can actually tweak it and get about 25 dB of gain at 10.368, this amplifier. And this is what I've been doing. What I did this morning, I did an exercise called Snowflaking. So let me zoom in and I'll show you. The idea behind the Snowflaking exercise is to add some stubs, some copper stubs. If you look closely, anything that looks like copper, I did add these strips in several locations. I tried different lengths. I repositioned, moved them around using a toothpick and some self-sticking copper foil stuck at the end of the toothpick. You can move the strip around and look at the output power. Like here, the input had to be retuned, and intermediate between the first and second stage, and then second to the isolator, and then isolator to the third. There's another piece here, and then even the output needed a bit of copper here added. Once it's stuck in place, you can coil it up, lift it from the surface, because these strips really couple to the ground plane. It creates a capacitive coupling and or a stub effect with an open transmission line at the end. So by playing with these different lengths, different position, you can optimize. It's a tedious exercise. It takes a few hours. Every time you want to permanently stick your piece, you shut off the power because you don't want to drop any of these on important places. You could just short out and then blow up transistors, and that's the last thing you want on such an exotic amplifier. So that's what the exercise is. Once you've positioned your things, they're stuck with the adhesive behind the foil. You can try to solder these in place for permanent mounting. That's what I did. I just tacked these strips with a little bit of solder. In some cases, it doesn't change anything. It's great. It tacks them in place. In some other cases, it hurts your output power once you solder them to the transmission line. Reason is they don't want a directly coupled link. They need a capacitive coupling to the track. So what I did in those cases, I put some Kapton tape on the surface over the existing trace and brought in my copper strip over it and then push hard so the Kapton tape acts as an insulator and it becomes a capacitive stub. And then once everything is in good location, I put a dab of elastic glue to hold everything in place so that over time with vibration things don't move. For those that are not soldered, I had to glue them down. It doesn't show because it's a transparent glue, but that's what I did. So that's the snowflaking exercise, and by snowflaking this amplifier I managed to get another 7 dB of gain and got my 25 dB of target gain. And this is typical of what you can get with these amplifiers. So I'm happy with the result. I will have a challenge driving this amplifier, still open for debate. There is a 3 dB attenuator right here. The white square is written 3 on it sideways, and that's a 3 dB attenuator. It will need a lot of drive here, probably around plus 15, plus 16 dBm, which is a lot of power, like up to 40 milliwatts. With the 25 dB of gain, I will be able to get maybe around 10 watts. This amplifier can be worked in a linear fashion up to 12 watts. After that, you can go up to 14 watts, but it's no longer linear. But 12 is a reasonable objective, 12 watt of output, but this will require around plus 15, plus 16 dBm of input, which is not easily achievable with small single type MMIC amplifiers on the previous stage. So I have this to resolve. Do I remove the attenuator to get another 3 dB of sensitivity on the input? If I do so, well, the attenuator is there for one reason, and it's usually to stabilize the input impedance of the whole thing. So that's one outstanding issue I'll have to think about. This amplifier is power hungry. You need to push around 70 watts of DC to get 12 watts of output. So if you do the math, it's not even 20% efficient. So it's very low efficiency. So a lot of heat needs to be dissipated. And the plate you see here is the heatsink, temporary heatsink mounted to the unit. You cannot run this amplifier for more than a few minutes before it gets too hot to the touch. So you need a heatsink of some kind, and forced air very likely. In a small enclosure, the whole system is going to put it. I'm going to have to put a fan to just move the air around, I'm pretty sure. For this exercise, I had a big blower here that, it's a 120 volt blower that I had that pushed a lot of air on the whole thing, including my 10 watt attenuator right here on the output, because I don't send this directly to my voltmeter, RF voltmeter, or the spectrum analyzer. I attenuate by 60 dB, 60. So pretty much the whole power is dissipated in heat during the tests. And this guy gets pretty hot as well. So that's the status. That's where I am with this 10 gigahertz power amplifier. It's promising. I have a few issues to resolve, such as the driving power in this thing, and then feeding so much power up on the tower, a lot of current at 10 volts. I'll have to think of a good plan. All for now. See you later. 7-3.